talking about energy, the major energy storage device that we know of is batteries, and the batteries exhibit very high energy density, but their power density is generally not that high, like a capacitor. So combining the best of a capacitor and the battery allows us to develop the so-called ultracapacitor or electrochemical supercapacitor. These supercapacitors, provide very high power density, but their energy density is not as high as batteries. But one of the goals in the research and development of supercapacitors is to get as much energy density as possible approaching the batteries. It may never be possible to achieve the same energy density as a battery, but even if you can achieve 20 to 40% of the energy density of a battery, it would be remarkable, because a major advantage of a supercapacitor compared to the battery is the charging time is very quick. Okay, batteries typically take hours to charge, whereas you can charge the supercapacitors within a minute or two. Besides the conventional consumer electronics and hybrid electric vehicle applications, the supercapacitors could be useful in running rovers and robots, whether they are micro-sized or macro-sized, because when these robots and rovers need to have quick start and stop functions, the power density of the supercapacitor could be useful. Again, nanomaterials such as carbon nanotubes and graphene have been shown to have much improved power density and energy density compared to the conventional graphite-based electrodes. There are novel ways of generating energy power. One is called thermoelectric effect, which exploits any freely available temperature difference. So here what you see is two distinct materials A and B forming two junctions, and when you have a temperature difference across these junctions, the so-called Seebeck effect can be exploited. The Seebeck effect relates the voltage or power generated due to the temperature difference across the junction. So the Seebeck coefficient S is voltage divided by the temperature difference. So there are a number of thermoelectric materials. Most of them are tellurides, such as bismuth telluride, zinc telluride, cadmium telluride, and then even in silicon and germanium. The efficiency of a thermoelectric material is defined by a coefficient called ZT, and the ZT depends on the Seebeck coefficient, which I mentioned, and then it's directly proportional to the electrical conductivity, and it's inversely proportional to the thermal conductivity of the material. So in order to get a high ZT value, we have to have high electrical conductivity and low thermal conductivity, but that is typically not possible because the electrical conductivity and thermal conductivity, they are more or less proportional. And so in order to obtain high ZT values, the thermoelectric materials are now being investigated in the form of nanowires, because in the case of nanowires, smaller the nanowire size, the thermal conductivity value goes down. So this shows a typical zinc telluride nanowire, a few nanometer diameters. So this is grown using a technique called vapor liquid solid, which I discuss in a separate lecture under inorganic nanowires. You can control the length and the diameter of the nanowires in the vapor liquid solid process. So the nanowire based thermoelectric devices, one can grow these telluride or other type of thermoelectric nanowires in a vertical fashion, very well aligned vertical nanowires with good control of the diameter and the height, and then you have PN junctions with the top contact and the bottom contact, and the gap between the nanowires filled with the polymer, which is all, there are thermoelectric polymeric materials such as polyvinylene difluoride, PVDF, they are available, and so this would be the configuration of a thermoelectric device, where the top surface could be hot and the bottom surface could be cold, and then the temperature difference is exploited to generate power. There are a variety of scenarios where the temperature difference is freely available, and then in many cases you can also take advantage of the waste heat and convert that into usable power. So the nanowire-based thermoelectric devices, there are a variety of applications beside aerospace. I just want to mention them, particularly even in civilian transport. When we fly at 10,000 meters or above, there is roughly about 60 to 80 degree delta T is available for free, because outside it's very cold and inside our plane there is a comfortable 20 degrees centigrade. So that temperature difference could be exploited using thermoelectric devices to generate power that could be used as an auxiliary power source inside the aircraft. And then computer chip cooling could benefit from thermoelectric device applications. So there are a number of other societal applications for thermoelectric power generation. And another type of power generation, this is actually power scavenging from vibrations. The earliest, this is done using a material called piezoelectric material. Piezoelectric materials, when you give stress or strain to these materials, that can be converted into a voltage signal, or vice versa. If you apply a voltage to the piezoelectric material, that can produce strain in the material. So the earliest patent on piezoelectric power generation, it exploited human heartbeat, and it showed a power of about 150 microwatts from 80 hertz heartbeats. So the vibrations can be used to generate power. One common possibility, of course this does not have anything to do with aerospace, but just to drive the point across that I want to mention, the human body routinely expends from 0.1 to 1.5 kilowatt doing a lot of different things, and if you can manage to harvest even a small portion of that power, it'll be very valuable. We normally exert about 130% of our body weight across our shoes when we are walking. So even at a roughly 10 to 12% of efficiency, so that can generate about 7 watts of power production for a person who's roughly about 65 to 70 kilos. So this type of few watts power production may not serve any large scale application, but it could still be useful in scenarios when there is no energy source readily available. That happens to be the case in space exploration. So taking advantage of vibrations and movements. So if we can get even small amount of powers, that could be used to drive sensors. For example, whether it is a temperature measurement sensor or a gas sensor that I talked about earlier on. So some of the common piezoelectric materials include PVDF, polyvinyl difluoride, lead, zirconium titanate, zinc oxide, aluminum nitride, gallium nitride, and lithium niobate. So these are all some of the common piezoelectric materials, and these materials are now, the research community, they're trying to grow them in the form of one-dimensional nanowires, and then try to construct them in the form of vertical nanowires used in piezoelectric devices. So these are some areas where the nanomaterials and evolving nano devices and systems and architectures could be useful for aerospace applications, besides the nanomaterial based composites, particularly carbon nanotube or graphene based composites, whether they are metal matrix composites or ceramic matrix composites or polymer matrix composites, which are very high strength but low density composites, that could serve to build the future spacecraft themselves.